Hello everyone, welcome to this webinar series. Silicon carbide provides many advantages over silicon and industry adoption is growing fast. One common challenge to upgrade from silicon to silicon carbide is the noise and EMI induced by faster switching speed, which in the meantime enables high efficiency and high switching frequency. In this video series, we're going to show you where our technology stands in the silicon carbide industry and share our recommendation to overcome the challenge of fast speed. In our last episode, we introduced the excellent figure of merits of Gen4 silicon carbide FETs to offer the low conduction loss, low switching loss, flexible gate drive, and best short circuit withstand time in the market. A lot of these features relies on the low RdsA of silicon carbide FETs. In this video, we'll dive into the device structure and explain why silicon carbide FETs has the lowest RdsA and benefits enabled by this structure. Silicon carbide FET is formed by a high-voltage silicon carbide JFET and a low-voltage silicon MOSFET in a cascode structure to deliver normally off behavior. The high-voltage silicon carbide JFET is a normally on device that requires negative gate-to-source voltage to turn off. The low-voltage silicon MOSFET drain-to-source voltage serves as the gate drive to turn on and turn off the JFET. For example, during the turn-off process, the low-voltage silicon MOSFET is turned off first and its drain-to-source voltage builds up. Once the MOSFET drain-to-source voltage is more than the JFET threshold voltage, the JFET turns off quickly and all remaining high voltage is blocked by the JFET. Here we illustrated how current flows in cascode for forward and reverse conduction. The left chart shows forward conduction where current flows in both JFET and MOSFET channel. The middle chart shows reverse conduction without synchronous rectification. Current flows in low voltage MOSFET body diode and JFET channel. The right chart shows reverse conduction with synchronous rectification. Like in forward conduction, current flows in both low voltage MOSFET and JFET channel. You can see whether in synchronous rectification or not, the JFET channel is always on, and the LV-MOS body diode has a voltage drop about 0.7 volt at room temperature. Therefore, silicon carbide FET provides very low third quadrant conduction loss, especially when synchronous rectification is not applied. With the understanding of cascode operation, we can now explain why silicon carbide FET has low RdsA. The left chart shows cross-section for the silicon carbide MOSFET, and the right chart shows silicon carbide FET in cascode structure. As we can see, silicon carbide MOSFET has a channel resistance which does not exist in silicon carbide trench JFET. Instead, the channel resistance is replaced by a low-voltage silicon MOSFET. And the channel resistance of silicon carbide MOSFET is much higher than that of a low-voltage silicon MOSFET, especially at a lower breakdown voltage. For example, at 650 volt, the silicon carbide MOSFET channel resistance can take up to 50% of overall on resistance of the device, while low-voltage silicon MOSFET only takes 5 to 10% of overall RDS-on. This is how our silicon carbide FET achieves such low RDSA. It's fundamentally rooted in the JFET. Thanks to the cascode structure of silicon carbide FET, we're driving a low-voltage silicon MOSFET which provides compatibility to all popular gate drive voltage levels, and a reliable silicon gate oxide that has been proven by industry over decades. There is no gate oxide in silicon carbide JFET. Like stated in previous slides, the cascode structure also enables lower third quadrant conduction loss when synchronous rectification is not applied, because JFET channel is always on. The silicon carbide MOSFET has a high voltage body diode that typically has much higher voltage drop. The silicon carbide JFET has no body diode, and the reverse recovery charge in the silicon MOSFET is very small because it is a low voltage MOSFET. Here shows body diode voltage drop of silicon carbide FET on the left and silicon carbide MOSFET on the right. Without synchronous rectification, when current is at 10 amp, silicon carbide FET has a voltage drop of 1.4 volt, while silicon carbide MOSFET has a voltage drop of 3.5 volt. Till now, we have introduced the benefits of Gen4 devices and how our technology enables these benefits. Next, it is equally important to share our recommendation and user guide so designers can fully exploit these benefits easily and reliably. Thank you very much for your attention. Please stay tuned for the next video.